Hi, and welcome to this video on circular motion, particularly circular motion with angles, be that banked curves or declined objects. Let's start by talking about what we're actually seeing here. Imagine you have a rope or an object on a string, and you take it and you start swinging it above your head like so. As you swing, it starts tracing a circular path around you, but there's a decline, there's a slight decreased angle here because you're not swinging particularly fast. As you start swinging it faster and faster, the line starts flattening out until you start getting something like this or this, and eventually it'll end up flat. How does this work? What's going on here? And that's what we're going to talk about today. And to start, we're going to start with this object here, this mass. In this example, we have a mass on the end of this. Let's say this mass is 0.250 kilograms. What are the forces acting on this? What do we need to know about this situation to know about this solved problem? Or to be able to solve this and understand what's going on here? Well, to start, let's talk about forces. In this case, there's only two forces. You have gravity pulling it down, and you have the rope pulling it up. This tension. And the two forces combined will give me everything that's going on. Now, if you're keeping this going at a constant speed, it's not moving up and down, it's going to stay at a flat level plane, so we can go through and do the rest of this problem. If we trace an angle here to our mass, we can find the force acting on it. We can measure all this out. And in fact, we can even see that this forms a right triangle here. Now, let's write our sum of all forces. So for this block here, pulling to the left, my sum of all forces x, and my sum of all forces y. These two forces, these two sums, tell me everything that's going on. In the x direction, there is no force acting, or at least no direction acting wholly in the x direction. But there is part of this force tension acting that way. Now, traditionally we say left is negative, so this would be negative force, which would give us a negative acceleration. However, to keep things simple, I'm just going to say left is positive for this example and make everything easy for us. In the y direction, I have my force tension in the y minus my force gravity acting on the object. Now, this is moving in a circle, so there's an acceleration. There's an acceleration pointing in towards the center of the circle, but this declined angle here means that it's not the only force. However, if you're moving this at a constant speed as you move this rope over your head, the height in the y direction will stay constant, which means that I'll have zero velocity in the y. In other words, my Ft in the y direction will equal m times g. And in the x direction, because I'm moving in a circle, m v t squared over r equals ft x. So now I have a way of relating these. I have two masses, I have g, I can really go through this. The question is, am I looking for the tension, the velocity here? And that ultimately depends on how you set it up. Experimentally, the easiest way to set this up, the easiest way to solve this is to do it yourself. Go forth, find a bit of rope, find a bit of mass the object, and swing it over your head. And time, how long it takes to complete one revolution. Now, a simple kind of follow-up idea to this. First and foremost, if we time it, we do it, awesome. But I can't have you do that and go through your problem that you're answering in your video. That'll be in your homework. For the video, so I went and did this. I took some measurements. The rope is 0.65 meters long, the drop was 0.2 meters, The mass was 0.25 kilograms, and I did one revolution, or one rotation, in 3 seconds. The question ultimately is, at that point, what's the tension in the rope? The drop here is 0.2, the length here is 0.65, 2.2 kilograms, and trip around 3 seconds. If you think you know how to do it, give it a try on your own. I'm going to go through it, and we'll have a practice problem after, but give this one a try on your own. So, first things first, I want to find this angle here. This angle will help me solve pretty much everything else. So, I have a triangle. This side is 0.65. This side is 0.2. Opposite hypotenuse tells me sine. Sine of my angle equals O over H, or 0.20 over 0.65. Which tells me my angle is sine inverse 0.20, 0.65. Gives me 17.92 degrees. Okay, now that I know my angle, there's several different ways I can go about solving this. I can find my velocity and get my ftx and go through this way, get my fty that way. I can find one and then get the other. I'm going to start by using my angle and get my ftx. So first things first, I need to figure out how fast this is going. What's its velocity? Because once I get that, I can get my ftx pretty easily. I also need to know what my radius is. My radius is not the length of the rope, it's actually this side here. So let's start by finding r. R is the adjacent side. So if I do adjacent over hypotenuse equals cosine, or I can say adjacent equals hypotenuse times cosine of an angle. My hypotenuse is 0.65. My cosine of my angle is at 17.92. So my radius in this case is 0.62 meters. Now that I have that, I can solve for my velocity. One revolution in 3 seconds. I need to get that in meters per second, so one revolution is 2 times pi times r meters, or in this case 0.62 meters. So my tangential velocity is 1.30 meters per second. Okay, so that's Vt, that's r, so I can plug it in here. 0.250 times 1.30 squared over my r, which don't forget is 0.62, gives me 0.68 newtons. If I talk about my force Fty, that's just m times g by this equation over here, which tells me that it is 0.250 times 9.8, or 2.45 newtons. But I'm looking for my total tension. Well, I have a triangle, I can just find the missing side. A squared plus b squared equals c squared, or in other words, ftx squared plus fty squared equals ft squared, or ft equals the square root of 0.62 squared plus 2.45 squared, which gives me a total tension of 2.54 newtons. Now, that's fairly simple. I could have also gone through, and once I had my force tension in the y direction, used the angle here to find my missing side. I could have done that same process with the ftx, because it's the same triangle using this angle here. Any way it would have worked. But the principle is all the same. Draw your free body diagram, find your angles, notice that your circle is still in the x direction, break up your non-aligned forces into components. Let's take a look at a practice problem. So here's a real-life application for you. You might have noticed before that in NASCAR or on overpasses, the pavement is banked or ramped in such a way to help the cars stay on the road. Because what this does is that instead of relying on friction to provide a centripetal acceleration, or just friction, the part of the normal force that is pointing to the right provides a centripetal force. That is, in other words, the force centripetal can be just your force in the...
Should say x direction here. That's a typo. I'll correct it later.
The problem with this is that when we go to solve one of these problems or talk about one of these problems, the issue comes up that our trick of rotating our coordinate grid doesn't work anymore. So if we want to talk about just the normal force, or if we even want to talk about having friction going down the ramp, because there's an acceleration this way, we need to align the grid to our acceleration, like so. Which means we need to be able to find angles and calculations. Now, there are a few tricks we can do to make this easier on us. First and foremost, when we used to rotate it, we'd line it up with the normal force. And we said this angle right here was 5 degrees. For those of you who remember your geometry, this angle here would then be 5 degrees.
By the vertical angle theorem.
Which makes it easier. We can break the normal force up now into x and y. As for the frictional force, we said that this would have to be a right angle previously, because it would be perpendicular to the ramp. And again, well, this is a right angle. This here, this green cross, is also a right angle, so the difference here has to be the same as the difference here, also 5 degrees. If you'd prefer, I could also prove it using the alternate interior angle theorem, but I don't think that's strictly necessary. But to start, let's keep it simple. Let's say there's no friction in this particular instant. How fast does the car need to be going around the curve to make sure in this particular instant that it is entirely being accelerated centripetally by the normal force? AKA, what speed do you need to be going so that this force friction here is not a factor?
Before you get going on that, some quick notes. First, the radius of this particular exit ramp is 50 meters. And secondly, I've made the correction from force normal y to force normal x, as I said would. Again, apologies for that mistake.
Okay, let's take this from the top. First thing I did is I crossed out the force friction since it's not a factor, just put a big X through it. And then I went through and wrote my sum of all forces. Sum of all forces y, sum of all forces x. I then split up my force normal into x and y values. Notice that I used the 5 degrees as the interior, which makes my y values cosine, my x values sine. Had I come over here, it would be 85 degrees, and then it would be sine cosine as normal. Either way you do it, you can go through and follow the green through where I solve. Notice how you're not accelerating up down, so this is still 0. And I get my force normal equals m times g divided by cosine theta. I keep going from there because my x direction is where my acceleration is. My a in the x direction is vt squared over r equals my force normal sine theta, again from up here in the left. I then plug in my values and solve. Force normal is mg cosine theta, mg cosine theta. I have m on both sides, so it cancels out. I then solve for v, and I get vt equals the square root of r times g times tangent, because sine over cosine is tangent. I then took that over here, plugged in my numbers, used my radius of 50, g of 9.8, and tangent of 5 degrees to get 6.55 meters per second. Or in other words, about 15 miles per hour.
And that's before factoring friction.
And because of that, you can get much higher speeds. This is why, again, they are inclined on both NASCAR and in exit ramps. Anyways, thanks for watching. Have a good day.